Hi everyone, my name is Ryan Chen, a grad student of Northwestern University. My poster is about the transition edge sensor chip design of modular CENNS detector for the Ricochet experiment. CENNS process means coherent elastic neutrino nuclear scattering process, which has been already experimentally measured by the coherent experiment at the spallation neutron source. So the goal of the Ricochet is to make a detailed measurement of CENNS spectrum at a nuclear reactor. The reactor has a flux of neutrino 1,000 times larger than the spallation neutron source. So to take the advantage of this high neutrino flux, we need to make a low energy threshold detector. We will use an array of cryogenic detector to perform a high statistics precision measurement. Our group is developing a transition edge sensor as a part of the Ricochet detector array. The TS-based detector couples a large volume of target, which is about 10 grams, to a thin superconductor film, which is about 100 nanometer. The superconductor film is the TS, which is biased to the transition, so it is sensitive to small energy deposition and could attain a low energy threshold. As shown in figure 3, the detector consists of 3 components. The first is the particle sensing target. It could be a silicon, germanium, or zinc. Second is the TS film. For this version, we will use a technology based on aluminum manganese film. The third is the electrical readout. We will use a squid readout system for this detector. On one of the surface of the target, there is a gold film deposited to collect phonons from particle scattering in the target, and a wire bond will connect this phonon absorber to the TS chip and transmits the heat. The TS chip plays a role as the sensor. The TS chip consists of 4 components. First is the wire bond. The wire bond connects the gold pads on the target and the gold pad on the chip to transmit the heat. And second is the TS film. The TS film translates the temperature change into resistance change. And the third is the gold meander. The gold meander is a thin gold trace which controls the thermal connection between the TS and the base. So we could optimize the length of the meander to control the decay time. And the fourth is the superconducting niobium traces and pads for TS readout. To optimize our design, we put up a numerical model to simulate the behavior of the detector. The model simplifies the detector into blocks connected by lines, shown in figure 5. Each block means a component of the detector, and the line between them means the thermal connection. We optimize the length of the meander for different target materials, and the figure 6 shows the optimization results. Lines are the ideal resolution of device which with a single heat capacity equal to the total heat capacity of the system. That indicates the theoretical best case of our device. Numbers near points are the length of the meander of this simulation. The goal of the simulation is to achieve a 50 eV trigger threshold with a decay time about 10 milliseconds. The TS chip are in production and stay tuned for new results. Here is one of our design of the TS chip.